Good morning, everyone. Today, we would like to report the results of our research, Generalization of Stern's Diatomic Sequence. First of all, let me introduce some background knowledge. Hyperbinary expansion is very important in our research. Here is its definition. In short, hyperbinary is very similar to normal binary, but each of its digits can be up to 2 instead of 1. You may look at the examples here. You can see that 4 can be represented as 100, 20, and 12. But in normal binary, 4 is only can be expressed represented as 100. You can see that the expansion is not unique. Secondly, Stern's diatomic sequence. Here is the definition. It's normal and simple, but it has some very interesting properties, such as it can construct a sequence that can run through all the positive rationals exactly one time. And the number of hyperbinary expansions is equal to, of n is equal to an plus 1, which can be calculated by this formula. So we are interested in this property and want to know what happens if we generalize this coefficient into any real number. And we also get some very interesting results here. Another direction of our research is hyper-H binary expansion. It's also very similar to normal binary, but each of its digits can be up to H, where H is an integer larger than 1. And we get 2 formulas to count the number of expansion. Before introducing our results, for convenience, we have this this definition, Bn and Ln. Bn is the number of 1 in the binary form of n, which is a well-studied sequence in OVIS. And Ln is log n base 2 and then floor. It is, which is 1 less than the length of the binary form of n. You may look at the examples here. There are 2 1s in the binary form of 5, so B5 is equal to 2, obviously. Then, why do we consider this sequence? Because we find that they appear in a special case, S is equal to 0. So it's natural to guess that it may be useful in the general case too. Finally, we can introduce our results. An, 2 formulas. We find that in our formula, An can be represented by A prime n, and A prime n has these 2 tidy and neat formulas. Of course, we can substitute the A prime n into the above, and we can get this complicated formula. But it can calculate An directly. Initially, our idea is that to solve the special case first when S is equal to 1, because we find that it's easy to calculate. In fact, we have 2 methods to find it. That's why we have 2 formulas. The first formula is that we find that the generating function for An satisfies this relation. This recursive relation. After an inductive method, we find that it can be represented as an infinite product. The trick is the expansion of this infinite product and the principle of turning a number into its hyperbinary form are exactly the same. For example, if we want to find a coefficient of x to the power 4, and because 4 is equal to 100, 20, and 12 in hyperbinary, these are the guidelines tell us how to expand this infinite product. For example, 101, 101, 101. 100 tell us we should choose this 1 times 1, and 20 tell us we should choose this and this one times together, and 12 tell us we should choose p to bx squared and rx squared. Then we can find px to the power 4 plus Rx to the power 4 and P.L.K to the power 4. Then we can get a coefficient of x to the power 4, which is A5. Then, similar to Stern's method, we can get the formula below. For the second method, we construct a function by using a parameter lambda. Then we find that they is satisfied this functional equation too. After that, we have to prove that they are equal to the generating function of an. Then after by comparing their coefficient, we can get the second formula. Then we solve the special case. After that, we have to find out the connection between the special case and our goal. The special case is when the coefficient of AK plus 1 is 1, which is solved, and our goal here. We observe this relation and prove it by induction. After that, we solve the general case completely. The next result is the infinite summation. Is very easy because we find it through the method of generating function too. But it's a typo here. It should be fx. It's different from the GS we mentioned before. The next properties in number theory is also very straightforward. We observe this pattern. Then we prove it by induction, and we find the final results by using the lemma here. Okay, here is the most complex part in our research, the hyper-H binary expansions. Recorded hyper-binary expansion is very similar to binary expansion, but its digit can be up to H. And we find two formulas to calculate it. Both of them are very interesting. The second one is about the multinomial coefficients. It makes sense because it is related to combinatorics, which can solve some counting ball problem. But the first one is related to, it invokes cosine. Yeah, it's very unexpected. We use two methods to solve the problem and find two formulas. The first one is very similar to the method mentioned before. We construct a functions by a parameter mu. Then we find that they are equal to the generating function of Hn. Then compare the coefficient. We can get the final results. The second one, we make use of Stern's method, which is mentioned in our reference. In addition, we use this lemma, the generalized version of Kummer's theorem. Then combine these two together, we can get the second formula. In the future, we hope that we can solve the cases like this, the 2x2 case, the 3x3 case, or even the n×n case. Also, there is some limitation, the time complexity. Maybe we can simplify those summation formula further, or the application of the property in the number theory. Because initially, we want a sequence that can run through all the rational function exactly one time by using these properties. However, as time is limited, we haven't finished. The deeper connection between with trigonometry, can we find a geometric proof for the formula that invokes cosine? That's a good question. Finally, counting other hyper number systems, can we find a method to count the hyperternary, hyperdenary, etc.? There are a lot of things for us to do. And that's all today. Thank you for your attention.